It's always a pleasure to be back in this beautiful city, especially for this event. I really like these Solstice summer schools. I think they're really arguably the best summer school in quantum foundations. So it's a pleasure to be here and tell you about how we should think about non-classicality in our world and in quantum theory. So I think it's safe to say that all of us here have heard at some point or another that quantum theory is weird and that it can't be explained classically. I mean, that's typically how it's introduced to us from the very beginning, like, look at all this weird stuff. But rigorously, what do we mean by this? What's the formal notion of classicality here? What particular part of quantum theory do we actually think is weird and mysterious? So over the years, people have pointed at very many different features of quantum theory. So wave-particle duality, entanglement, the no-cloning theorem, teleportation, quantum interference, uncertainty relations, a long list of phenomena are often kind of pointed at, and it's like, this, I don't understand how to explain this. So that's the part of quantum theory that's confusing. Or what about this part or that part? But the problem is that typically when people say those things, they're not backing up those arguments with any sort of rigorous formal principles or arguments. It's sort of just based on their intuition or what sort of models they can think of to explain what's going on. And that's a dangerous thing to do because, as we've seen, a lot of those things that historically have been viewed as mysterious actually can be given a simple classical explanation, where all the systems that you're studying have definite properties, and all the particles are moving along definite trajectories, and there's nothing weird or mysterious or quantum going on. So for example, we saw how in the Speckens toy theory, you can have non-commutativity, complementarity, interference, no cloning, teleportation, entanglement. All of these things, in and of themselves, are not necessarily hard to explain classically. There are classical models, like the one we saw, which can reproduce all of those features at their most basic level. So if we really want to pinpoint the part of quantum theory that's actually mysterious, then we need some better approach. We need a principled way to divide the phenomena into the ones that can be explained classically and the ones that cannot, the ones that are rigorous proofs of non-classicality. And you might ask, okay, but why bother? If we already know the world is quantum, then do we really need to look backwards and try to understand sort of what does classical physics tell us? If that's not the true theory of the world, maybe you might think this is just some taxonomy problem. But I'm going to argue, no, this is really important for quantum foundations. And a first reason is one that is tied in with what Rob was saying, that quantum theory, it's often given to us as, oh, it's the thing in the textbooks, it's a finished theory. But it's not a finished theory. There's many realms of physics and science more broadly where we don't know how to apply quantum theory. So quantum gravity, quantum causal modeling, machine learning, thermodynamics. Rob had an even longer list of areas in which we don't know what the consequences of quantum theory are. And so maybe it's not surprising that we don't have a quantum theory that applies to all of these regimes if we don't even understand the boundary between classical and quantum physics in the other realms where we do know how to apply quantum theory. So another reason to study the boundary between quantum and classical is to understand resources for quantum information processing. And so this is kind of a pragmatic utility. And it's almost tautologically clear that we need to study non-classicality if we want to achieve kind of quantum advantages. Say you're trying to build a device that you want to outperform all quantum devices. Outperform all classical devices. Well, to do that, you better know what the scope of all possibilities within classical physics is. Otherwise, you don't have any assurance that you've really done anything genuinely beyond genuine advantage from quantum theory. And a final reason to study non-classicality is just the intrinsic interest of the matter. I think it's just true that since the advent of quantum theory, there were many parts of it that you look at and they seem initially mysterious. And we want to understand, are those real mysteries or can we understand them? And maybe just a silly way to sort of kind of judge interest in a topic, you can go look how many hits it gets on Google Scholar, and you can see that non-classicality, even since the 1920s or 30s, there's just many people who have studied these questions, which things have classical explanations and which things don't. Okay, so to begin with, I'm going to recap this framework for theories that Rob talked about, the framework of generalized probabilistic theories. And the reason I'm going to do that is because within that framework, there's kind of a privileged classical theory. And we can ask then sort of which phenomena can be reproduced within such a privileged classical theory. So as Rob talked about, This is the framework for generalized probabilistic theories, which is sort of a landscape of possible ways that the world could have been. Each point in this framework is a different theory, a different hypothetical world. And one of these worlds is the quantum world, one of them is a classical world, and that we have box world and all these other possible worlds. So we're studying these not as genuine empirical competitors to quantum theory, because we know that quantum theory, at least in most regimes, is the most predictive theory that we have. But we study these theories so that we can compare and contrast. And here we're going to be doing a lot of comparisons to the classical theory, because we're trying to understand classical explainability. So at the highest level, what these theories are is just some collection of systems. These are the physical degrees of freedom that you're going to study, and a collection of processes, which are like the states, transformations, and measurements in the theory, and a composition rule, which tells you how you compose different systems, different processes, and so on. And in particular, if you compose a lot of processes to form a complete experiment, then the theory should give you some rule for making predictions about the observable probabilities. So for example, if I have this kind of simple experiment where we have a state, so a state in the theory is a process with no input, but which has an output. So we have here we have a system, and this is a state on that system. And then a transformation is something that maps one system into another. And then finally, we have measurement effects, which are what you get when you do a measurement and you condition on one particular outcome. And when you have a kind of complete experiment, this is just one example of a circuit depicting a simple experiment, then the theory tells you how to make predictions, such as the probability that the effect will occur given the transformed state. And of course, more broadly, you can generate much more complicated kinds of compositions. Maybe your experiment has a lot of components, and when you consider any sort of complete experiment like this, described as a circuit in this theory, then the theory should tell you how to make predictions for that circuit. And kind of a familiar example is quantum theory as a GPT. So here, the systems are associated with Hilbert spaces. Or to view it as a GPT, it's more proper to view the system as the set of linear operators on the Hilbert space. And Rob talked about kind of what that looks like for quantum theory. You can form a basis for the qubit space with the identity X, Y, and Z Pauli operators, for example. But in general, we just have some vector space of linear operators on the Hilbert space. That's a system. And the states in the theory are density operators. The transformations in the theory are completely positive trace-preserving maps, which of course take density operators to density operators. And then we have effects, which are operators, which are measurement operators. So a measurement is a POVM, a positive operator valued measure. And if you pick one particular positive operator, then that's an effect in this theory. And we know how to compose processes like this in quantum theory. So the probability that you'll see this particular effect, given this channel and this quantum state, is just what you get when you trace the measurement effect with the transformed state. So that's just viewing quantum theory as an example of one of these GPTs. Another GPT that we have some familiarity with is the classical theory. So you can think of this as the theory where the systems are just sets. So you have a set of possible states of the system. If you like, you can think of it as sort of a variable that ranges over the elements of that set. And a state in this theory is a probability distribution over that set. A transformation is a stochastic map which acts on the set, and consequently it takes a probability distribution to another probability distribution. An effect in this theory is just something that maps these states into probabilities, numbers between 0 and 1. So we call these response functions. And we also know how to compose processes and compute the probabilities. So the probability rule in this theory is just classical probability theory applied to these stochastic processes on the set. So here, this is just the law of total probability, where we see the probability of getting this particular outcome corresponding to this response function is what you get when you have some probability of preparing the system in the specific state lambda, and then times the probability that that lambda gets transformed stochastically into lambda prime by the transformation, times the probability that that lambda prime leads to that outcome, and then we just sum over all the possible lambdas and lambda primes. So that's just the law of total probability. So this whole theory is just essentially a representation of classical probability theory, sort of at this informational GPT level. And So those are two examples of GPTs. We saw a lot of other examples in Rob's talk. And I want to focus on sort of what are the distinguishing features of different theories of different GPTs. And there's two kind of essential features of a GPT. You have the convex geometry of the theory, of the space of processes within the theory, and you have the compositional structure of the theory. And these are essentially, all the properties of a theory can be read off of these two kinds of features. So the convex geometry was one that we saw in Rob's talks. He talked about how the particular shape of the state space for quantum theory on a qubit is a ball, and that's a different shape state space than for Spekkin's toy theory, and the particular convex geometry encodes a lot of the features of the theory. So there's a number of ways you can see that. For starters, remember that the way you compute probabilities in a GPT, when you have this sort of vector representation of the states and effects, is you take the inner product of the states with the effects, if you want to compute the probability of a given effect on a given state. And those inner products obviously are going to depend on the particular vectors in the theory. So all of the observable probabilities are encoded in this convex geometry. Moreover, you can sort of just see the uncertainty relations of the theory are sort of baked into that geometry as well. So on a qubit, for example, you see that the maximum predictability of measurements in x, y, and z are sort of jointly constrained. You never have any points all the way out on the corner of this cube in the same way you do for box world, because you have this constraint that x squared plus y squared plus z squared equals 1. So you can see the uncertainty relations are written into the convex geometry. The incompatibility relations are written into the geometry of the effect and measurement spaces. So the different geometries of the state space, the effect space, and all the channels, the spaces of the transformations as well, contain a huge amount of information about the theory. But then there's other kinds of information as well, which is the compositional structure. So this would be like, for example, if I consider a state on a pair of systems, you can ask, does the theory allow for things like entangled states? Or are all the states in the theory separable? What kind of entangled states are allowed? Similarly, for the effects, do you have entangled effects? And if so, what kind of them? That has to do with how systems compose in the theory. And another kind of compositional structure is if you compose two particular transformations, like T1 and T2, which particular third transformation do you get in the theory? It has to be something in the theory so that the theory is closed in a consistent fashion, but different theories might say that T1 composes with T2 to give a different third transformation. And in fact, the entire kind of rule that tells you how to compute probabilities from a complete circuit can be viewed as just a kind of rule for composition. You could see that sort of the composition rule here in the classical theory was just like matrix multiplication of those stochastic matrices. And so the way you compute probabilities is just baked into that composition rule, for example. So these are the two basic kind of features. If you change the convex geometry, you're changing the theory. If you change the compositional structure, you're changing the theory. And so we're interested in playing around with those different features and seeing what we can learn. And I want to note sort of that a lot of what I'm saying, almost everything I'll say throughout my lectures, can be applied to either GPTs or to what I'll call GPT fragments. So a GPT I'm viewing really as a whole description of a theory, a possible way the world could be, whereas a fragment is just a description of some particular experiment, or it's just a subset of a theory, basically. So the GPT contains all possible systems, processes, and circuits in your sort of hypothetical world, whereas a GPT fragment can just be any subset of those systems and processes and circuits. So this fragment is more what you'd use if you're trying to describe a specific experiment you've done. And so I'm going to ask not just about classical explainability of a theory, but also you could talk about just classical explainability of a fragment of a theory, which would be like of a particular experiment. And everything I do will kind of work for both of these sort of simultaneously, so keep that in mind. As I mentioned, this is more like describing a possible way the world could have been. This is more like describing an experiment. Okay, so now our question is, which theories in this landscape of possible theories can be explained by the classical GPT? And which experiments, which fragments of an arbitrary theory can be explained? So if you take quantum theory, for example, you might guess where this is all going. The entirety of quantum theory will not be explainable by the classical GPT. But if you look at some particular experiment within quantum theory, That's just a fragment, a subset of quantum theory, and many such fragments will be explainable within the classical GPT. So that's why it's interesting to kind of separate out these two questions. So what is the answer then? What kinds of GPTs or fragments of GPTs can be explained by the classical GPT? Well, intuitively, the answer is the ones that fit inside the classical GPT in a structure-preserving way. And I'm going to now formalize that for you. So we say that there's a classical explanation for the GPT, again, or a fragment, if you can find some map gamma from the GPT into the classical GPT, where this map has a number of properties. First of all, obviously, it should preserve the predictions of the original GPT. It should be linear, and it should be diagram preserving. I'm going to break these parts down now for you. So the first thing, let's think just about the domain of the map and the codomain of the map. So the thing that we're trying to represent is this given GPT, or fragment. So within the GPT, we have some systems, and we have some processes on those systems. And we're trying to represent those, so we're finding a map into the classical GPT. So that mapping takes the GPT system to some classical system, a system in the classical theory. So it takes GPT system A to some associated classical variable, or set, if you like, lambda A. And it takes system B to some lambda B. And it takes the transformation from A to B to a transformation that is a substochastic map, because that's what transformations are in the codomain, the classical GPT. So it takes you to a stochastic map from the associated input variable to the associated output variable. And this stochastic map we can just represent as a conditional probability distribution from this set to that set. So that's the kind of form of the map we're looking for, but it needs to apply to sort of every different type of system and every different type of process. Here I'm just showing it for one sort of generic representative. And the next condition is that this map has to preserve the predictions. And again, this is pretty obvious. If you want to be explaining the original GPT, well, then it better be that the probabilities assigned to any complete circuit in the original GPT are the same after you apply this map. So when you compose the processes in the representation, all those classical representations, and you use the classical probability rule, it should reproduce the predictions of the GPT circuit with the GPT probability rule. And then the last two conditions, we had linearity and diagram preservation. So what are these conditions and why do we need them? Well, remember we said there's two basic types of features of a GPT that sort of tell you everything about it. There's the convex geometry and the compositional structure. And these two assumptions just tell you that you want to preserve that structure. So linearity is exactly what you need if you want to preserve the convex geometry of the theory. And diagram preservation is what you need to preserve the compositional structure of the theory. So that's what makes this a good explanation. If it wasn't linear or diagram preserving, it would just be taking some of those key features that make the theory what it is and just throwing them away. It would be scrambling all of that information. We're going to demand that all that information is preserved in the classical explanation, and that's why it's a good explanation.
Yeah,
question?
So linearity isn't it a more narrow condition than convexity, or is it just equivalent?
You could weaken. Yeah. So the question was sort of, do we need to assume full linearity, or can we just assume convex linearity? And you can show that they're equivalent. So you could just assume convex linearity here, and from that you could sort of linearly extend to full linearity without loss of generality. Yeah. But you're right that physically, really, what we need here is convex linearity. Okay. So what do I mean by linearity? Well, first of all, remember this is a mapping from a whole space of processes. So like every process in the GPT or in the fragment gets mapped into the classical representation. And we know that sort of processes in a GPT live in a vector space. We saw examples of that for quantum theory, where you have the vectors in the block ball. Those live in a vector space. We're mapping into this classical process theory where the things also live in vector spaces. So we're just talking about a linear map from a vector space to a vector space. And in particular, that means that if you have certain linear relations that hold among processes in the GPT, those will have to be preserved under this mapping. So take, for example, quantum theory. If that's your GPT, we know there's certain linear relationships among the states in the theory. For example, the equal mixture of 0 and 1 is the same as the equal mixture of plus and minus. And so this constraint under a linear representation will imply a constraint in the classical theory. So remember, the states in the GPT get mapped to probability distributions over the set associated with the system. So this state 0 gets represented by some probability distribution over some lambda. And this state gets represented as a different probability distribution, and then we have the representations of the plus and minus states. And by the assumption of linearity, we have that the relationship between these probability distributions has to be the same as this relationship between the states that are being represented. And similarly for every other sort of equality that holds among the GPT processes. So that's just what follows from linearity. Diagram preservation is just the assumption that sort of whatever your circuit structure is in the GPT, it gets mapped to the same circuit in the representation. So if this is sort of the GPT experiment you're considering, then this state gets represented in particular as a state here. So we can think of this as sort of a lot of separate maps, if you like. So this system in the GPT gets mapped to a system in the classical theory. That's pretty common sense, right? The system doesn't get mapped to something else, like a transformation. A system goes to a system, a state goes to a state, a transformation to a transformation, and so on. So it just tells you to preserve the sort of compositional structure that you're working with. And so now, to kind of put this all on one slide, you have some experiments that you're interested in. Those are depicted by these circuits on these GPT systems and GPT processes. We're looking for a linear map into circuits of the exact same shape, but where now all the systems are just random variables, and all the processes are just substochastic matrices. And if you can find such a mapping for all possible circuits in your theory that reproduces the predictions using this, the composition rule within this classical theory, namely just composing your stochastic matrices together, that's a classical explanation. So this, in a single slide, is basically the notion of what it means for a GPT to be classically explainable. Where, again, you kind of have to test this for all possible circuits and for all possible states and transformations within all the circuits. If you're interested in a GPT fragment rather than an entire GPT, then you would, rather than ranging over all circuits and all possible elements of each circuit, you would just range over the ones that appear in your experiment. But otherwise, it's the exact same notion. Yeah?
I was wondering, isn't it kind of a strong requirement to conserve the same structure? Don't we just need to have a possible mapping that brings the same initial states mapped, obviously, to the same results in the end? Why do we need to keep the same structure?
You're saying why assume linearity, basically?
Yeah, basically.
Yeah. So first of all, in the next talk, we're going to see what happens when we drop linearity. So that's a good question. But what linearity buys for you is that the explanation is a much more compelling explanation. It preserves all of the features of, like all the features that you can read off of the geometry of the state and effect spaces. If you don't demand linearity, those can all just get completely scrambled. And so it's not as good of an explanation. You can also motivate linearity through Leibniz's principle, which I think I'll say some about at the end of this lecture. But yeah, so we'll come back to that question sort of from several different angles as we go forwards. Any other questions? This is sort of the basic definition, so now's a good time for clarifying.
What would a map look like that does not preserve diagrams? Like, hard to imagine.
I completely agree. The question was, what does a map look like that doesn't preserve diagrams? And I don't actually have a good example of what such a map looks like. It's as you said, it's hard to imagine. But I think there are some examples within the computation literature. Like if your goal is not to explain what's going on, but just to kind of provide an arbitrary mathematical simulation, then I think there's kind of some sort of holistic models where if you add a single gate, if you add a sort of single gate at the end of the computation, then the entire structure of the simulation changes in this really big holistic way. And whereas here, in this kind of representation, if you add a single thing, then it will just add a single stochastic process at the end. So it's sort of this modular description. So yeah, there are such examples, but not really in the foundations literature that I'm aware of. Yeah. Any other questions?
Can you go back? Can you go back one slide behind?
Yeah.
Yeah. So in this explanation,
Mm-hmm.
on the right hand, left hand, does the mu sub 0, mu sub ket 0, and mu sub ket 1, these two variables of lambda, are these two the same, actually the different entry of the large lambda.
Yeah, so these two are quantum states on the same system in this example, and therefore they're associated with the same lambda, so the same sort of space of classical states. But this is a particular probability distribution over that space, and associated to the second quantum state will be a different probability distribution over the same space.
Sorry, I'm a bit confused. So for these mu's, they share the same lambda, that's random variables.
Yeah.
But, so what's your point by distinguishing them by using the different subscription?
Well, the mu is a probability distribution over lambda. So the representation of this quantum state will be a particular probability distribution over lambda. The representation of this quantum state is a different probability distribution over lambda.
It's more like
The-
mu of ket 0 given by lambda. No, sorry, mu of lambda given by 0, mu of lambda given by 1. Is that the way to...
Yeah, that would be another way of writing this, exactly. And intuitively, all that we're saying is sort of, in the classical theory, you can think of these as the possible properties of your system, and we're saying that the quantum state gets represented not as a particular set of properties, but as a probability distribution over the possible properties of the system, just like we saw in Spekin's toy theory, and as Rob sort of motivated in his talks. Okay. So an example of this that some of you might be familiar with is the Wigner function in quantum theory. It's a particular representation of quantum theory when the Wigner function happens to be everywhere positive. So the Wigner function is a linear map from quantum processes to real-valued vectors. Here's what that linear map looks like for the quantum state. If you give me a density operator rho, I compute this particular integral, which you can see has a parameter x and a parameter p. So once you finish computing this integral, you have a function over x and p. And to each different density matrix, you'll get a different function. That's the Wigner representation of the density matrix. And similarly, you can represent transformations and measurement operators. So you're getting this kind of representation of quantum processes as functions over a phase space. Now, in general, these functions can go negative, so you can't interpret them as stochastic processes in some classical theory. However, if for some specific experiment, you find that all of the procedures in your experiment happen to be associated with Wigner functions that are positive everywhere, then you can just renormalize those processes, those functions, and view them as probabilistic representations over the phase space. And in that case, this is just an example of one of these classical explanations that I've been talking about. But critically, and maybe I'll mention that all of Gaussian quantum theory, for example, can be represented positively in the Wigner representation. And that's a huge fragment of quantum theory that includes entanglement, no cloning, teleportation. All of these things are possible within Gaussian quantum theory, and yet they have this simple classical explanation. But here, we're kind of generalizing the idea of, I shouldn't have used the word non-contextuality yet, because I haven't introduced it. This definition of classical explainability that I've introduced generalizes this idea from this specific linear function to arbitrary linear functions. And it generalizes from this specific set of classical variables, x and p, to some arbitrary classical variables. So it's a much more general notion of classical explainability than the Wigner function, but it shares a lot of the same sort of similarities. So the Wigner function is just one example of such a classical explanation. Okay, so now I'll connect this to this topic that you may have heard of, which is called generalized non-contextuality. So the notion of classical explainability that I've defined for you so far is equivalent to the idea of a generalized non-contextual model. I'm not going to spend too long on this, but if you're interested, I gave 3 hours of lectures at the last edition of the Solstice Foundations where I went into a lot more depth about non-contextuality and the connections with what I'm saying here. So today I'm only going to spend one of my lectures on this topic, so if you want more details, I think that's a great place to start. But to kind of motivate this a little further and to get back to the question about linearity, why do we assume linearity and how do we motivate all this? Well, we can motivate both the notion of classical explainability that I introduced so far and also this equivalent notion of generalized non-contextuality using a principle in the philosophy of science due to Leibniz known as the identity of indiscernibles. So he said, if a difference in some setups is not distinguished in the observable phenomena, even in principle, there's nothing you can do to distinguish them, then it should not be distinguished in the ontological picture either. And so this is a methodological principle that you can use to guide you in constructing physical theories, and it's one that I'm going to argue has been very successful in constructing physical theories throughout the history of physics, and therefore it's a good principle that we should continue to expect to hold and use to guide us when we're constructing theories. So some examples of how this theory has been applied successfully in science. So Einstein used this in his arguments for special relativity, where he considered if you have some sort of absolute rest frame, then there's a physical difference between these two scenarios, where there's a magnet moving through a fixed wire versus a wire moving over a fixed magnet. If there's a privileged reference frame, then these can be distinct physical situations. But you see that there's no difference in the observed phenomenon, namely the current that is induced to go throughout this wire. And so Einstein argued we should get rid of this privileged reference frame and make these two situations ontologically the same, as a consequence of the fact that they're empirically the same, even in principle. There's nothing you can do to tell them apart. He also used similar considerations to say that in this kind of famous elevator thought experiment for the strong equivalence principle, he was arguing that if you're in an elevator that's accelerating versus sitting at rest in a gravitational field, there's no observable experiments you can do to see the difference. And so he was motivated to build a theory that baked that into the ontological picture as well. And so he used this principle kind of repeatedly throughout his works to build some of his best theories. So it's a very powerful principle that has led us to some really good theories. Yes? Question?
Thank you. Yeah, so I just wanted to say that this principle has got a bit of a dark side, and the thing like a whole argument when it can actually make you kind of lose the reality in your physical theory. How well, basically because of the strong equivalence principle, you can have two different stress energy tensors which give you the same space-time, but they have different but they are like related to different matter. So it's kind of it's sometimes kind of dodgy to use it too much.
I don't think that's right. I'm not an expert on this, so I think afterwards you should talk to Rob, who has actually written a paper on how, also for the study of the whole argument, Leibniz's principle, I think, has been used effectively as opposed to leading to problems. But I'm not an expert, so let's defer that till afterwards. What's the article's name? If you look for Rob Speckens and Einstein, Leibniz, it's something about like the significance of Leibniz's principle in the philosophy of physics or something like that. Yeah. Okay, so how is this principle relevant to us here, and how does it motivate this kind of classical explanation that I've been talking about? Well, remember I said that we're assuming linearity, which means that constraints like this one here turn into constraints in the classical explanation like this. And this is just an instance of Leibniz's principle, because you can see that this top equation here is just a representation of some in-principle indistinguishability that's baked into quantum theory. Namely, if you prepare a quantum system in this particular density operator, so if you prepare either the 0 or 1 pure states, and you mix them with equal probability, well, that's a different way of preparing the system than if you instead prepare the plus or minus pure states and mix those with equal probability. And yet, because of this equality, they're the same density matrix, which means they'll always lead to the same predictions for any measurements you can do, right? Because the Born rule only depends on the density matrix. You take the trace of the measurement operator with the density matrix, and it's the same density matrix on the right and the left, even though in the laboratory it's very different things you'd be doing. So this is sort of an in-principle indistinguishability that's built into quantum theory, and Leibniz would tell you you should try to explain that in any good model that's supposed to somehow reproduce this phenomena. Any good model would have, because of this in-principle indistinguishability, there should be sameness in that explanation. And so here we see that's exactly what we're demanding in this particular kind of explanation, namely a classical explanation. So this is motivated by Leibniz's principle. If you didn't have this linearity, then you wouldn't be respecting Leibniz's principle. Okay. So now I'm going to move to kind of trying to give some geometric intuitions for this idea of classical explainability. So I'm going to start with the simplest possible scenario, which we call a prepare-measure experiment. So in this circuit, we just have some different possible ways of preparing the system in question and some different possible ways of measuring it. And so we're ranging over different states and measurement effects here. And let's first ask, what does the classical GPT look like in this particular prepare-measure circuit? So we need to talk about the states in the theory and the measurement effects in the theory. So in the classical GPT, the state space always has a particular geometry, namely it's a simplex. And the effect space always has a particular geometry, which I'll call the dual of the simplex. So what do I mean by those? Well, a simplex is just a triangle or an n-dimensional generalization of a triangle. And a dual to a simplex is just the set of vectors whose inner product with the vectors in the simplex is between 0 and 1, so like valid probabilities. And we can see that the dual to a simplex will always be a hypercube if we sort of think about a kind of convenient coordinatization here. So let's put the vertices of the simplex on the unit vectors. So here I'm depicting this as an example in dimension 3. So we have 3 sort of unit vectors, and the simplex is just the triangle formed by the convex hull of those 3 points. And then it's not hard to see that the set of vectors whose inner product with those 3 vectors and everything in their convex hull is always between 0 and 1 is just the unit hypercube, like this. So this is the classical state and effect space for a classical system that has 3 possible states that it can be in. And sometimes it's easier to just focus on the normalized states. This is what Rob was doing when he mentioned that sort of the state and the effect space, they differ in dimension by 1. Because you can see here, if I just plot the normalized states, then this space of effects is 3-dimensional, whereas the space of states lives in 2 dimensions. If we also plot the subnormalized states, like this 0 vector here, and then take the convex hull of all of those, then they both live in the same dimension. But it's kind of easier just to think about the normalized states, so let's do that. And you can kind of see now that this is just a representation of a classical statistical theory, because the set of states in this theory is isomorphic to the probability distributions over a set of classical states, namely the set that corresponds to the vertices of this simplex. So in this case, you can just think of this as a theory where you have 3 possible states of your system, and each point in this triangle corresponds, it's in 1-to-1 correspondence with the probability distribution over those 3 points. So this point here uniquely decomposes as the equal mixture of these 2 vertices, and it has 0 weight on this vertex. This point here in the center is uniquely associated with the probability distribution that's uniform over all 3, and similarly for every point in this space. And so in other words, every mixed state in this theory, every non-extremal state, decomposes into pure states in a unique way. And that's very different from quantum theory, right? In quantum theory, if you take a mixed state, like the maximally mixed state, there's an infinite number of ways of decomposing it into mixtures of pure states. Like the 0 mixed with 1 is the same as plus mixed with minus. In this theory, what's special about the simplex is this exact property. So this is why the state space of a classical theory always is a simplex. It's so that you're just a representation of the space of probability distributions. And you have this particular property, which conceptually, what this property implies is that you can always imagine that there is some true state of the system. It's either here, or here, or here. And anytime you have a mixed state, it's just because you have uncertainty about the true state. And that's sort of a unique interpretation, unlike in quantum theory. Similarly, if you look at the space of effects and the space of measurements, I'm not going to go through this in detail, but in this theory, all logically possible measurements are physically possible and compatible. And what that means is that there exists a kind of super measurement, like the perfect measurement, that tells you exactly what the state of the system is, and it does so without disturbing the state of the system. And these are kind of the things you expect from a classical theory, right? Like this, you always are in a definite state, you might have some uncertainty about it, but it's still in a definite state, and you could do a measurement to learn exactly what the state of the system was. So that was kind of the geometric representation of the 3-dimensional classical system. Maybe it's worth taking a step back and looking at the 2-dimensional classical system, which is maybe the more familiar one. So in this case, a simplex is just a line segment. So you can think of like the 0 state and the 1 state of a bit, just 2 possible states of a bit, and this is just the set of all possible states of knowledge over the bit. And then measurements form a kind of square, which is a two-dimensional hypercube. And we can get a little more intuition for this by noting that every simplicial system, every classical system, fits inside quantum theory, obviously, right? Because classical theory is like a limiting case of quantum theory. And so for the bit, if we embed this bit into the block ball on a qubit, well, we have these classically distinguishable states 0 and 1. Obviously, those are going to form antipodal points on the block ball. And now the measurement effects are part of this kind of top-like figure, the ice cream cone that Rob showed in his plots. And here you have sort of the measurement effects that pick out the pure state, and then you have the zero effect and the identity effect. And that's where that shape comes from. Now, I wish I could show you what it looks like to embed this classical three-dimensional system into quantum theory, but unfortunately you can't embed it into a qubit. You would need a Hilbert space of dimension 3 or more to embed 3 perfectly distinguishable states. So in general, these higher dimensional classical systems, if you want to embed them into quantum theory, of course, you also have to embed them into higher dimensional systems, and I can't draw that for you on a slide. I don't know exactly what that geometry looks like, but yeah, it will contain, of course, each of these simplicial systems. So at this stage, I've kind of introduced the classical GPT. It's privileged. It has these special properties that make it kind of our representation of classical probability theory. Henceforth, I'm going to try to remember to call that the strictly classical GPT. And it's just the simplicial GPT, the one whose state space is a simplex, and which has these other properties I've been describing. And now we want to ask more broadly, what are the classically explainable theories or fragments? It's not just going to be this one particular GPT, but it's going to be more broadly anything that fits inside this one particular GPT. So any theory or fragment that fits inside the simplicial GPT, we're going to call it classically explainable. And this is just a special case where I'm focusing on only the states and measurements in the theory of that earlier definition I gave for classical explainability. So in particular, we're going to look for a linear and diagram preserving map from the given GPT or fragment in this simple prepare measure scenario into the classical prepare measure scenario. So kind of intuitively in a picture, if my GPT or fragment is described by this blue region, so these are the states and these are the effects, well, you can see that in this example, just by construction, it fits inside the simplicial theory of dimension 3, and therefore this experiment or theory is classically explainable. And I want to note that the way you interpret this diagram will depend on whether you're thinking of this blue regions as a theory or as a fragment. So in particular, notice that this blue region does not completely fill out the space of classical states and effects, which means these regions in white, they're not in the theory or experiment. Now, if you're doing an experiment and this blue region is the description of your experiment, that's not too exciting. That just says your experiment didn't access any perfectly extremal states or perfectly extremal effects. In fact, any experiment will have some noise, so you'll always have some regions here that are outside of your experiment, but inside the logically possible space of states and effects. But if you're saying this is actually your theory, this blue region, now you're saying not only did you not access these points, but they're in principle impossible to access. So that's a little bit more subtle and interesting. But in either case, you would say that this theory or experiment is classically explainable. Okay, so let me formalize that now for you. So here's our experiment of interest. We're asking for a linear and diagram preserving map into the classical circuit of the same form. Now, by diagram preservation, we can break this up into sort of 3 separate parts. The system in the GPT has to get represented by some classical set, which I'm going to call lambda. These are like the hidden variables, if you like, the classical states of the system. The state gets represented by a state, namely a probability distribution over lambda, and the effects get represented as response functions. So that's diagram preservation. And now, so we say then, a prepare measure GPT or fragment is classically explainable if and only if there exists a pair of linear maps, right? So we see now, because we're looking for a map from effects to effects and from states to states, we're looking for a linear map here and a linear map there. So we want a linear map taking states of the GPT into a simplex, and a linear map taking effects of the GPT into the dual to that simplex in a way that the inner products are preserved, so the probabilities are preserved. And if we have this, we call it a simplex embedding, just for the obvious reasons. Although actually it's not a perfect name, because notice you need to embed the states into a simplex, but also you have to embed the effects. So you could call it like a simplex dual embedding, but this is a bit shorter. So if I give you some generic GPT, just at a glance, you might not be able to see immediately from the geometry whether it can be embedded into a simplex in the dual. So it might not be obvious from inspection whether this thing is classically explainable or not. But you can go about looking. So you go about asking, can I find a linear map into the simplex and a linear map into the dual? Well, the first thing you should note is there's a lot of freedom in a linear map, right? Like, you could jointly rescale the states and the effects. If I make the states smaller by a constant factor and the effects larger by a constant factor, that's not going to change the inner product. So that doesn't change the GPT at all, but it will change whether or not you can embed it into any particular simplex and dual. Similarly, you might need to jointly reorient the states and effects. So if you rotate them all in the same direction, it's also not going to change the inner products. And in fact, you could do any linear transformation to the states if you apply the inverse of that linear transformation to the effects. And once you do all those sort of arbitrary, kind of check over all those arbitrary possibilities, if you then find that it fits inside a simplex and its dual, then you know that it's classically explainable. But there's a little bit of a catch here, which is that the diagrams I've been showing you are kind of suggesting that you only need to check into a simplex of the same dimension, right? I here keep using this example, but in general, there's nothing wrong with an embedding into a higher dimensional simplex. That would just mean that the number of classical states is greater than the sort of number of, than the dimension of the given GPT. And that's perfectly fine. And that makes it a little bit harder to check. Now you have to check sort of for the existence of these linear maps in arbitrary dimensions into these higher dimensional simplices. If you ever find one, you can stop searching. But if you don't find one, then you have to keep looking. And that might make it sound like it's quite hard to figure out whether your GPT is classically explainable or not. But luckily, actually, you can show that this problem, you don't have to sort of go one dimension at a time. There's a more clever way to check, where you just run some linear program, which is kind of an efficient program you can run on your computer to check whether this given geometry is simplex embeddable or not. So now we have kind of the tools we need to assess whether our given experiment or theory are classically explainable. And we can use these intuitions to kind of prove things easily now, just by thinking geometrically. So for example, we can prove that for any theory or any experiment, it's going to become classically explainable if you add enough symmetric depolarizing noise. So depolarizing noise is when you just shrink all the states or effects symmetrically. And to see this then, you can basically choose some simplex that's big enough to contain your effect space, your state space. So for any state space, there'll be some simplex that's gigantic that fits around it. So pick that simplex. Of course, if it's a huge simplex, then the dual, this hypercube, will be really small. So it might be a tiny little cube inside your effect space. But now, as you apply your depolarizing noise, it's just going to shrink the effects further and further, and eventually they're going to fit inside the hypercube. So you can see, just basically by this kind of simple geometric argument, that every theory under sufficient noise becomes classically explainable. And in fact, you could use this as a way to define a measure of non-classicality, like how much depolarization did it take to make your GPT classically explainable. If it took a lot, then your theory was really very non-classical, whereas if just a little bit of noise already makes it classically explainable, then you didn't have very much non-classicality to begin with. Okay, and we've already seen an example of one of these classically explainable theories. Yeah, question?
Sorry, David. Because before, when you said about the trade-off between making your states... Sorry, thank you. Before you said about the trade-off between making your state space larger and your effect space smaller and stuff. But now I just wondered, when you apply the polarizing noise, why does just the effect space get smaller and you don't have to adjust anything regarding the states?
Yeah, so there's kind of a lot of symmetries to this example. Like, if you chose the depolarizing noise to be on the states instead, then you could just run the reverse argument where first you put the hypercube around the effects, and then you see the state shrinking. So yeah, there's kind of some symmetry here that I've just broken by picking a particular
Okay,
choice.
but then it preserves the normalization of the probabilities.
Yeah,
Right.
as long as you're kind of doing things jointly, then all that matters is the inner product. So
Okay, thank you.
yeah, thanks. Okay, so we've already seen an example now in Rob's talks of one of these classically explainable theories, the Speck-and-Toy theory. So to see his theory to show that it's simplex embeddable, consider the simplicial GPT now of dimension 4. So what's the 4-dimensional generalization of a triangle? It's a tetrahedron like this. And you can construct the Speck-and-Toy theory by picking the midpoints of the edges of this simplex and then taking their convex whole. So that defines this octahedron living inside the tetrahedron. And this is exactly the GPT state space of the Speck-and-Toy theory, and the effect space can be constructed similarly. So you kind of see, geometrically, by construction, this thing is just living inside the classical GPT. So it's classically explainable, it's simplex embeddable. And moreover, for any sort of simplex embeddable theory that you have like this, you can kind of work backwards. So imagine you'd never heard of Speck-and-Toy theory, but you just had this GPT and you wanted to think about it sort of ontologically in this realist picture. Well, then you could go about saying, okay, let me just take each of the vertices of the simplex to be possible classical states of some system. There's 4 of them. So I'm just going to think of that as maybe there's some, I could label those as like x and p, each of which has a value 0 and 1. That's just a conventional choice. You could also just call this state 1, 2, 3, and 4. But in any case, you have 4 possible states of the system. And each of these midpoints in the GPT corresponds uniquely to a probability distribution over those 4 true states, those 4 ontic states of the system. And so if I label things this way, then I have these 6 probability distributions like this. And that's exactly the probability distributions from Speck-and-Toy theory. So this theory is the one that you get by imagining that these are the states of maximal knowledge in the theory. So in particular, we say that everything outside of this octahedron is not possible. So like this point out here would be the one corresponding to the probability distribution, to the probability distribution where you know that it's exactly this ontic state, but that one's not in the theory because we're only living inside the convex whole of these 6. And as Rob talked about, these 6 states turn out to be very much analogous to the quantum states shown here on the block ball, the stabilizer states. And consequently, this theory can reproduce a lot of those features that these stabilizer states exhibit, even though we're working within this simple theory where everything can be interpreted as having kind of some definite states of reality. All of the sort of interesting features that you see coming up in Speck-and-Toy theory are coming because the states of maximal knowledge, the pure states in the theory, the extremal states in the theory are these sort of non-maximal probability distributions, right? None of these is the point distribution on the ontic states. They're these, they're spread out, and in particular, they overlap with each other. And so I've just tried to kind of suggest that any simplex embeddable GPT or fragment can be viewed similarly. You can work backwards to construct a sort of ontological model for that GPT. In every case, you just imagine that the vertices of the simplex correspond to the ontic states, and then every GPT process is just a stochastic process on those ontic states, and you can uniquely read it off from the simplex embedding. So any simplex embedding gives us an ontological model of the GPT. So now another way of thinking about it, if you want to remember this going forwards, a classically explainable GPT is just one that admits of an ontological model, as I've defined them. And the only sort of interesting thing here is that if this blue region is really representing a true theory, then as in Speck-and-Toy theory, there's these regions that are logically possible states and effects, right? They exist in the classical theory, but they're outside of the posited explanation. And so these particular regions are kind of ruled out by an epistemic restriction like the one that Rob introduced. If we're talking about experiments here and classical explanations of them, then we don't even have to say anything like this. This is only if you kind of want to view it as a full theory. Then you need kind of this principle that tells you why certain parts are logically possible but not physically possible. Okay, so in summary, we have 3 kinds of classes of GPTs. We have the strictly classical ones that I'll call simplicial. They're defined by a simplex and its dual, one for each dimension. We have the simplex embeddable GPTs, which are defined in the same way, but together with an epistemic restriction that rules out some of the parts of the simplex and its dual and says those are not in the theory. And then we have all the other GPTs that are not embeddable into a simplex. This, as I've mentioned, this is the classical theory, so I'll call it the strictly classical theory. All of these GPTs are still classically explainable. They're still consistent with the same sort of ontological underlying story. And the remainder of the GPTs, we'll just call them non-classical. These first two GPTs, I've sort of vaguely argued, although I haven't gone through it in detail. They don't have any contextuality. They're consistent with Leibniz's principle, whereas the last class of GPTs do exhibit contextuality. And as we saw, even though this class of GPTs is classically explainable, it can reproduce all of these phenomena that in the past were thought to be mysterious. So now we see they're not so mysterious after all. And the strictly classical theory does not exhibit these phenomena. Rather, it has these privileged properties that we talked about earlier. What about these non-classical GPTs? Well, that's where all the good stuff lies. If we want to see what is unique to quantum theory and what is actually hard to explain and where we should look for quantum information processing advantages and kind of all the novel physics, we shouldn't be focused on these concepts. We should be focused on things that can only be exhibited within this class of GPTs. Things like contextuality, computational speedups, non-locality, and some other more nuanced phenomena. And I'll say more about these sorts of things going forwards. Is it time for a break yet? I think so. Any questions? Yes.
Okay, so to be clear, then the classical theory doesn't admit things like teleportation or entanglement. It's only specific things that you can embed within the strictly classical theory that will permit these supposedly quantum effects that aren't actually quantum effects.
Yeah, that's right.
Okay, right. That was just clarification. Sorry.
Yeah. So I've now kind of defined for you what I mean by classically explainable for both theories and experiments. And I want to now give you some examples of non-classical phenomena and what we can learn from them. So a first kind of thing we could ask is, what is non-classical about quantum state discrimination? Now, usually, if you ask that question, this is what you'll hear. You'll hear people say, well, in quantum theory, there's no perfect single-shot discrimination of non-orthogonal states. So if I give you a quantum system, like a qubit, and I tell you, look, this is prepared in either the state 0 or the state plus. Those are non-orthogonal quantum states. And I ask you to guess which one I prepared. Well, they're not orthogonal, so there's no single measurement you can do that tells you exactly which one. You can get some information by choosing some measurement, but there's no measurement that perfectly will let you answer that question. And people often say this is in stark contrast with a classical world, right? Many people say this is evidence of non-classicality. Because think about a classical state, like a chair. Well, a chair in two different states, position 1, position 2, you can just look at it and you can see in a single shot whether it's at position 1 or position 2. So that seems like maybe a difference between quantum and classical theories. But in fact, this is completely backwards. So what I'm going to try to convince you of is that it's easier to discriminate overlapping states in quantum theory than it is in any classically explainable theory. And so my claim is the following. If you take two states, which have some overlap here, and you plot the probability of success at this discrimination task in quantum theory versus any theory that is any one of these classically explainable GPTs that I've introduced, then you find that the classically explainable GPTs have this bound, this linear trade-off relation that bounds how well you can discriminate those overlapping states. And quantum theory has what's called the Hellstrom measurement, which achieves the bound shown above it in blue. And so you can see that quantum theory gives you an advantage for state discrimination. It's actually easier to discriminate these overlapping states. So how can this be? What's wrong with this intuition about chairs and how easy they are to discriminate? Well, the usual argument is based on a bad analogy. Namely, when I look at this chair being at position 1 or 2, those are totally non-overlapping classical states. Of course they can be perfectly discriminated. If I go to non-overlapping states in both quantum and classical theory, you can perfectly discriminate totally orthogonal states. That's not something that's special about classical theory. It's true of both classical and quantum theory. So the analogy, the appropriate analogy, is to consider overlapping states in a classical theory. So that might be a little confusing if you think about the chair. So let's start with the Speckens toy theory example. Here we saw this is a classically explainable theory, and we had these extremal states of the theory which have some probabilistic overlap. And so these states can't be perfectly discriminated. What does this look like in the chair example? Well, think about two different ways of preparing the location of the chair. Either I sample from some probability distribution over positions, or I sample from a different probability distribution over positions. And then I place the chair at wherever I sampled. And then I tell you, guess which probability distribution I sampled from where to place this chair. Those are two different ways of preparing the location of the chair. And now, if these are overlapping probability distributions, well then whenever the chair is in this overlapping region, there's nothing you can do. There's no measurement on the chair that will let you guess which distribution I used to sample the chair. And so these are ways of preparing the chair, just like ways of preparing a quantum system, that have some overlap. And if you compute the maximum probability of success, as I mentioned, you find that in quantum theory, you actually have an advantage. So it's the complete opposite of the usual intuition. Quantum theory doesn't make it harder to discriminate unknown things. In the face of uncertainty, quantum theory helps you to discriminate things. And in fact, it's the same story all over again if you look at quantum cloning. The usual story that people give is that, oh, there's a no-cloning theorem. That's what's non-classical. This naive take is just, oh, in a classical theory, you can copy information, and in quantum theory, you can't. Isn't that weird and mysterious? Well, again, that's actually not the most sensible answer, because in both classical and quantum theories, if you know the state, if you have sort of information about what the state is, you can perfectly copy it. If you tell me the quantum state is the state 0, I can just prepare you 100 copies of it. Similarly, in a classical theory, you can copy known information. But in neither theory can you copy information when you have some uncertainty about what the state is. So you can't clone probability distributions in a classical theory, as Rob sort of alluded to, just like you can't clone unknown quantum states. And in fact, unknown states are easier to clone in quantum theory than they are in any of these classically explainable GPTs. So once again, you can just compute the maximum probability of success in any GPT that's simplex embeddable, and you find that it's this particular curve here. And in quantum theory, you can do better at cloning. So again, it completely flips the standard intuitions.
How do you compare like a classical notion of state overlap with the superposition notion of quantum mechanics? Like,
that's a great question.
You said, like, we have two classical distributions and they are overlapped, but I don't know if this can be said to be true.
That's a great question. Yeah. So the question was like, how do we compare overlaps in one theory versus another? Because in quantum theory, there might be a natural way to compute an overlap between two states, but in a classical theory, you're no longer talking about density operators, but rather probability distributions. There's a number of ways you could go about it. One, you could try to cast both theories into the GPT framework and then use a common notion of overlap, since they're now both described within the same vector space framework. The way that we actually did it when we computed these plots was we operationalized the notion of overlap by introducing measurements that perfectly discriminate one of the two states and then seeing what that measurement gives for the other state. So there's kind of a few different approaches. I think whichever one you take, you're going to get something similar to this. But it's a good question. Yeah. And so those are the two examples I'm going to go through in detail, but you can kind of run the same sort of analysis on whatever physical phenomena you're interested in, right? If you like to study interferometers, well, then you can ask, what is non-classical about interference? The mere existence of interference is not in of itself evidence of non-classicality, because we see interference in things like the Speckens toy theory or in any of these other simplex embeddable theories. But you can show that some particular trade-off relation between path distinguishability and fringe visibility, for example, is evidence of non-classicality. If you're interested in uncertainty relations, again, you can show that there's some specific nuanced features of uncertainty relations that are witnessing non-classicality. It's not the mere existence of them, but rather the specific form of the trade-off relations. And you kind of can run through all these and start to build some insight into what is really distinctive about quantum theory. And when you do this, a kind of pattern starts to emerge that we like to call the thin film of quantumness. So this is the idea that unlike how it's usually presented to you in a classroom where you're kind of handed this thing and you're told from the beginning, like, look at all this weird stuff, the uncertainty principle, it's crazy, no cloning, unbelievable. Really, most of those things actually are classically explainable. The bulk of the phenomena, in some sense, are classically explainable, and if you want to see the genuine non-classicality, you kind of have to get out to the outer reaches, like the most extremal edges of the theory. And you can kind of see that if you look at like the gap between quantum and classical, here where we have some numbers, you see it's on the scale of like a few percent. You know, you can get an advantage for cloning of, you know, maybe at the maximum it's something like 10%. But it's not like every time you copy information, you're witnessing non-classic, or every time you fail to copy information, you're witnessing non-classicality or something. No, the majority of the phenomena are classically explainable, and it's really kind of, as I said, the outer reaches of the theory where you see the genuinely interesting stuff. And our goal in studying these kind of simplex embeddability and non-contextuality is to really zoom in on this boundary between classical and non-classical. And that's where we expect to see the interesting parts of quantum theory beyond that sort of divide. Okay, a final topic, which I'm just going to cover at a kind of high level to give you a sense for what you'll often find in the literature if you're looking at, like say you're doing an experiment and you want to test. Well, one way you could test whether it's classically explainable or not is you could find the GPT description of everything you did in the laboratory, all the states and measurements, and then you could just check the simplex embedding condition. And I mentioned that we have kind of efficient ways to do that. There's another way, which is historically been more common, although it's no better or worse, it's just a different way, which uses non-contextuality inequalities. These are kind of analogous to Bell inequalities, which we'll talk about later this lecture. So the way that you compute non-contextuality inequalities, well, first you choose the particular experiment of interest. Again, I'm going to focus on this prepare measure case, and I'm going to label the preparations by P, the measurements by M, and the outcomes by K. And you could start by finding sort of the GPT representations of all those processes. So maybe it's quantum theory, and you find that my experiment used these particular quantum states, or maybe it's something else. The next thing you do is you find the identities that these satisfy. So all the sort of linear constraints that hold among the states and the measurement effects and the transformations in general. Whatever your processes are, you can, just by doing a bit of sort of simple matrix manipulation, you can compute all of these different equalities that hold among the processes in your theory. It's not too hard to do. Here's just one particular example, but there will be many others as well. And then from each of these, as we discussed, linearity will give us a constraint on any potential classical model. So you write down the list of all of these constraints, and now I want to notice that these conditions are experimentally observable. You can check whether these things are empirically indistinguishable from those things. So this is sort of an equation that we can test. This equation is not something you can directly test, right? Because it's referring to these potentially hidden variables. It's kind of this proposed classical model. It's not necessarily something you have any direct evidence of. So this is kind of a hypothesized constraint on a hypothesized model. And so what you want to do then is you want to do some mathematics, which we now have sort of systematic tools for, that kind of reduce this system of equations you get, all of these constraints, to some equations that only refer to the empirical data. So again, I'm not telling you how to compute this, but you can go from these unobservable constraints to some observable constraints. So this is just a constraint on the observed data, the probability distribution over outcomes in your experiment. And you can see in this particular case, it's like a linear trade-off relation between these probabilities, has to be bounded by some real number r. And these are called non-contextuality inequalities. So the data from your experiment is just some list of real numbers, right? As you range over p, k, and m, you get these observed probabilities between 0 and 1. We can throw all of those into a vector, right? Just a vector where we kind of, the indices of that vector are k, p, and m. And then that means your entire experimental data is just a single point in this high-dimensional vector space, right? The dimension of the vector space would be the cardinality of k times the cardinality of p times the cardinality of m. So in this space, kind of that vector of probabilities is just a single point. And for that point to obey this constraint, well, this is the equation of a hyperplane. So this just says that this point has to be on one particular side of a hyperplane in this space. And I'm going to draw this all in 2 dimensions as a little cartoon. So this is, in 2 dimensions, this is just the equation of a line, right? And it says that this point is on one particular side of the line. And now if I look at a different non-contextuality inequality, now I have to be on one side of that line, and that line, and that line. And you put all these constraints together, and it picks out some region in the space of observable probabilities, and we call that the non-contextual polytope. So if you do your experiment, and you find that the data corresponding to your vector lives inside this polytope, that means you satisfy all the inequalities, and that means that you know there's a non-contextual classical model for it. If, in contrast, you find that your data violates one or more of those inequalities, so you live outside the polytope, then that's your rigorous proof of non-classicality, according to the definition that I gave in my earlier talk. And famously, quantum theory predicts that some of the correlations will be, in some experiments, outside of this polytope. But I want to emphasize that if you find correlations outside of the polytope, that's a proof of non-classicality that doesn't assume the correctness of quantum theory. Quantum theory tells you where to look to get these violations, but the derivation of that polytope at no point assumes the correctness of quantum theory. And that's nice because it means these proofs of non-classicality are kind of robust to future theory change. If quantum theory is overthrown by some theory of quantum gravity, it'll still be the case that all the times you thought you had non-classicality, you actually did. Okay, and I think I already sort of said that. So that's the end of the first talk, and now I'm going to switch to talking about a different kind of non-classicality. I'll just mention there's a number of references here if you're interested. I would recommend starting rather with these series of extended lectures from the last summer school. There's actually not a huge amount of overlap between what I said today and in those lectures. So I think they would be useful. But I'll pause for questions before moving on to this. Yeah.
Okay, thank you for the talk first. So I have a question regarding this non-contextual scenario. So there is also the formulation of contextuality from the KS theorem, which also was briefly discussed before. But I wonder, from this formulation, that as far as I understood, is an ontological formulation, which are the cases that are considered in this scenario, more general scenario, that are not considered from the KS contextuality? So that's my first question. I have another one.
Mm. Yeah, so if you ask me afterward, I can tell you a lot about the connection between Koch and Specker and generalized. But broadly speaking, to get a proof of Koch and Specker contextuality, you have to assume determinism, which we're not assuming here. And you need quantum systems of dimension 3 or more, whereas here, even on a qubit, there's such proofs. Also, Koch and Specker only considers the structure of measurements in quantum theory. So you can't get a proof that only looks at the structure of states, for example, whereas here, kind of we're looking at the entire experiment rather than just the structure of the measurements. Right. So there's kind of a lot of ways in which you can see non-classicality much more broadly here. Koch and Specker is really about this one specific aspect of quantum theory, namely the structure of projective measurements.
Yeah. Okay, thank you. I might ask you later more. So just to close with another question related, is can we formulate also a polytope from the KS kind of contextuality, or just from this point of view?
Yes, I believe there are polytopes of relevance. I mean, there's a bit of contention about how you experimentally test Koch and Specker non-contextuality because they assume determinism, which is a bit of an idealization, and they assume projective measurements, which is also an idealization. But I think there are sort of polytopes that they study in those contexts. And there's also going to be polytopes in the study of Bell scenarios that we're going to get to soon.
Okay, thank you.
Thanks. Yeah.
Hi. So I was kind of wondering about like the main motivation. I don't exactly understand why do we want to define this classicality and non-classicality through this, in the sense of like which things are like classically explainable and which aren't. Like I'm asking mainly because like in physics we see a lot of situations when we can have two competing theories and one of them is going to explain the same things in the other, but is going to fail some other to explain some other phenomena, and then we typically choose the one that explains everything. And I'm kind of see that this kind of seems a bit similar to these cases.
Yeah. So I mean, for starters, I'd refer you back to the slide where I gave sort of 3 different motivations, but let me just re-summarize 2 of those motivations. I kind of think of it often as there's a motivation for like looking backwards and a motivation for looking forwards. The looking backwards motivation is over the last 100 years, there has, any way you slice it, there's been a long, essentially never-ending debate about, is wave-particle duality mysterious? How should you understand, what ontological conclusions can you draw from the existence of complementarity and the Heisenberg uncertainty principle and the delayed choice quantum eraser? So even just to kind of clear up all of those historical debates, I think this is exactly what you have to do. And so that's sort of the looking backwards, just cleaning up the past. I think looking forwards, what this is most good for is sort of the pragmatic front. If you want to understand where to find sort of advantages of quantum over classical computing, technology, et cetera, then as I mentioned, you sort of need to know the boundary between what is sort of all possible things you could do in a classical world or not. And that kind of helps you build intuitions for what kind of information processing protocols you can get an advantage for from quantum theory.
Yeah, so exactly what I meant is like, why do we think that the fact that something can be explained by some abstract classical theory that exists in some space of classical theories is enough to say that this phenomena is not quantum, or it is classical or classically explainable? Like the very fact that like there could be somewhere some theory, why is it enough?
So I'm not sure I understood the question. So here we sort of, I mean, kind of by definition, we worked within a framework for theories, and we asked sort of which things can be or cannot be reproduced within the classical theory. So insofar as you agree that that's a good notion of, insofar as you agree that we've got the right classical theory and we have a good notion of what it means for an explanation to be an explanation, then it sort of just follows. But yeah, I'm not sure I understood the question.
Okay, we can just talk later about it.
After, yeah. Yes, one more.
Before, where in the final slide, when you list all the different properties that you can derive from symplectic embeddable, non-symplectic embeddable, okay. Under the symplectic embeddable, there was complementarity also. And usually, when I think about complementarity in the, at least in the usual way Bohr initially introduced it, I have always linked it to contextuality. But maybe I don't know, or have not clear what you mean here by complementarity and contextuality.
Yeah,
so I was a little bit, it was strange for my usual intuition to see complementarity on one part and contextuality on the other. But
yeah, that's a good point. That word has meant many different things to many different people. And in fact, that can be true of some other, well, possibly some of these others as well. So maybe what I should have written instead is sort of like incompatible measurements, the existence of incompatible measurements within the theory. That's what I had in mind when I wrote it down. Yeah, Bohr meant something very different and very, just different from when he said complementarity. Okay. All right, let's jump through. Okay, so next we're going to move to a particular kind of non-classicality, which I'll call Bell non-classicality. It's non-classicality in a particular kind of scenario. So this was kind of the schematic we had for what a classical explanation looks like, this linear and diagram preserving map into the classical GPT. But now I'm going to ask what happens if we relax that assumption that the mapping has to be linear. So now we just allow sort of any old mapping. Just, is there any collection of classical processes, which might be totally unrelated to the processes over on the left, which can reproduce the statistics in the original causal structure? The only thing we sort of preserve here is we still demand diagram preservation. So it's the same causal structure in the GPT as it is in the classical representation. So it's still a non-trivial constraint, but it's a much weaker constraint. So obviously, because it's a much weaker constraint, it's a lot easier to construct such representations. So for example, in a prepare-measure scenario, you can always reproduce all the correlations for any GPT with any observable correlations. But in more general causal structures, it turns out that sometimes it's impossible to construct even such a relaxed representation. And if you do manage to build one of these representations, but it's a nonlinear representation, well, then it's not a classical explanation in the usual sense, certainly not in the sense of the definition I gave in my previous talk. In particular, it doesn't say anything about all of the features of the theory that come from the convex geometry. All of that will just be completely not explained by your description. And so really, we're not, and furthermore, Leibniz's principle that we argued is a good principle for, that we should demand of a good explanation, that will be completely violated by such representations. And so we're not really interested in the case where you can succeed in finding such a model. It's hard to take these models seriously as good models, but what's interesting is that sometimes, even under this relaxed set of assumptions, you can prove that there's still not such a representation. So in other words, we're kind of going to use this as a necessary condition for the existence of a classical explanation. In particular, if you can prove that there's no mapping, well then obviously there's no linear mapping, which means you have a proof of non-classicality in the sense I already introduced, and it's an especially strong kind of proof because you've assumed even less. And the famous example of this is Bell's theorem. So this experiments kind of implementing a Bell test were awarded the Nobel Prize just a few years ago, and this is kind of one of the most interesting and beautiful results in physics. Let's get into it. So imagine you have two parties, Alice and Bob, and they share some systems, which I'm going to now take to be quantum systems. And I'm going to denote quantum wires by these double lines like this. So that's how you can remember that they're quantum systems specifically. And these two systems, Alice has one, Bob has the other. They might be prepared in some potentially correlated state, might be entangled, for example. And now Alice takes her system and she does a measurement on it. So a measurement is something that takes in a system and it spits out a classical outcome. And I'll label that classical outcome by A, and I'll denote it by this single wire like that. And in fact, we might imagine that Alice can choose among some set of measurements, and I'll label her choice of measurement by X, and I'll depict her sort of input measurement setting by this single wire like this. And then similarly, we can have Bob choosing among some set of measurements with outcomes B and measurement settings Y. So this is what's called the Bell scenario, when you have these two parties doing local measurements on some potentially correlated system. And my claim is that the correlations you can predict and observe in quantum theory for an experiment of this sort are a strict superset of the ones you can observe in the same causal structure, but where everything here is described by the classical GPT. So I claim that there's no such mapping, even if we forget all about linearity. And that is one way of framing Bell's theorem. So let me prove, we're going to spend now the next 15 or so minutes proving this theorem. So let's start by asking, in this classical case, where everything here is a classical system and a stochastic process on those classical systems, what are the kinds of correlations you can observe, the most general correlations? Well, let's start with the simplest case, where each party has two choices for their measurement, and the outcomes are binary outcome, which means that the cardinalities of all four of these variables are 2, so I can just take all of them to be either 0 or 1 valued, just as a convention. Now, the observable correlations in this scenario are just a probability distribution over the outcomes, A and B, given the measurement settings X and Y. And we want to find out what is the most general form of these sorts of probabilities consistent with this assumed causal structure. So first, let's label the classical systems here. I'm going to call them lambda 1 and lambda 2. And as we've said already before, a state on a classical system is just a probability distribution. Here, it's a probability distribution over lambda 1 and lambda 2. So it's a potentially correlated joint distribution. This process here, well, it's a stochastic process that has 2 variables as input and 1 variable as output. So it's a stochastic map from x and lambda 1 to A. And we can just associate that with some conditional probability distribution, P of A given x lambda 1. Similarly, on Bob's side, we have P of B given y and lambda 2. And now we just apply classical probability theory to compute the most general form of this correlation within this circuit. Well, it's given by just composing those 3 stochastic processes. So we multiply them and we sum over the unobserved lambda 1 and lambda 2. So again, that's just the law of total probability. And so now we have a particular form for the correlations of interest, and this form just followed from the assumed causal structure. And my claim is, from this form, we can deduce some constraints on these correlations. So in particular, the first constraint you can deduce from this correlation is that the probability distribution over B, if we just look at B, that distribution will be independent of x. So P of B given xy is just equal to P of B given y. How do we see that? Well, first of all, let me define this distribution, P of B given xy. That's what you get if you take the correlation and you marginalize over A. So you just sum over all the possible values of A in this expression here. Well, if you do that, you see there's only one term that depends on A, right? And this term is a probability distribution over A. So if we sum it over A, it just goes to 1 like any probability distribution would. So this term will die when we sum over A. And then you'll notice there's only a single term left that depends on lambda 1. So when we sum over lambda 1, this joint distribution just turns into the marginal probability distribution P of lambda 2. So this sum, then, we're just left with this term here, which is unchanged, and P of lambda 2. And we're still summing over lambda 2. So that's all just from summing this expression over A. And you can see now it doesn't depend on x, as promised. So this object here is just some P of B given y. So this constraint is called the no signaling constraint. It says that for somebody who doesn't know the value of A, there's no correlation between x and B. And that's good because that's what ensures that Alice can't superluminally signal to Bob faster than the speed of light. Like, if you imagine these two parties are far apart, Bob doesn't know A when Alice first gets her measurement outcome. And if there was some dependence here on x, then Bob could see the change in his distribution over B depending on what Alice chose for x. But here, because of this constraint, we see that doesn't happen. And that just follows from the assumed causal structure. Similarly, we have, of course, the no signaling in the opposite direction, which just says that the marginal distribution over A is independent of y. There's further constraints, which are still more interesting, and I'll call this constraint here a Bell inequality. So this is an example, one way of writing the CHSH inequality that's named after the 4 people who first derived these inequalities. So this inequality says that the total probability that the outcomes A and B have a sum mod 2 equal to the product of x and y. So this is a particular kind of correlation that I'm claiming is bounded by 3/4. And to derive this, I'm going to assume, just for simplicity, that x and y are equally likely to take either of their possible values. So let me write that out more explicitly. First of all, let me remind you what the sum mod 2 looks like. So this is an operation on 2 bits, which says if the bits are the same, like if they're both 0 or both 1, then the sum mod 2 is equal to 0. If the bits are opposite, then they sum together to get 1. So this is just the parity function, if you like, on 2 bits. So writing out this inequality a little more explicitly, we have 4 possible cases, because x and y can be 0, 0, 0, 1, 1, 0, and 1, 1. And I'm assuming each of those happens with probability 1/4. So now I want to sum the total probability that the outcomes in the x equals 0, y equals 0 case have to be the same. Why do I need this expression? Well, take a look here. So when x and y are both 0, the product of x and y is also 0. And we saw then that a plus b, in order for that to equal 0, the bits have to be the same. So we want the probability that the bits are the same in this case. Similarly, if we have the x equals 0, y equals 1 case, it's still the case that the product of x and y is 0, which means we still need a plus b to be 0. So we need the 2 bits to be the same. And in the third case, when x equals 1, y equals 0, it's still the case the product of them is 0, so we need the outcomes to be the same. But in the final case now, you see when x equals 1 and y equals 1, now the product of x and y is equal to 1. And so we need the bits to be opposite so that their modular sum here is equal to 1. So this is the expression that we've derived, sort of, that's what I meant by this left-hand side here, but expanded a little more explicitly. And that, I'm claiming, will be bounded by 3/4. That's what we want to derive. So far, I've just claimed it. And the way to derive this, let's temporarily assume determinism. So let's assume that the outcome A is just a deterministic function of lambda 1 and x. Of course, we see in this diagram, this is a general stochastic matrix, so we could allow for that, but for now, let's just assume it's a deterministic function. And in that case, we can talk about in a given run of the experiment, lambda 1 and lambda 2, they're just classical variables. They have a definite value in each run of the experiment. So given those particular values for lambda 1 and lambda 2, there will be, we can think about the value assignments to the outcomes A and B. So there will be some definite fact of the matter in this, under this deterministic assumption. There's a definite fact of the matter about what outcome A you will observe for either x that you choose. Right? Nature already knows what answer it will give before you ask. So I'll indicate that by A0 and A1. And there's also some definite fact of the matter about what outcome B will get for whichever y you choose. And I'll call those value assignments B0 and B1. Of course, in any given run of the experiment, you can only observe 2 of these 4 values. You can't see both A0 and A1, because you have to choose x as either 0 or 1. But in a deterministic theory, all 4 values are predetermined. And to make this expression as large as possible, we want each of these terms to be equal to 1, right? The largest a probability can be is 1. So if we tried to make each of these terms equal to 1, what would go wrong? Well, we can see what goes wrong by considering this graph here, where I write down the 4 possible value assignments to Alice's outcome and Bob's outcome given the 2 possible settings. To make this first case true, we need that in the x equals 0, y equals 0 case, so that's the 0, 0 case is here and here, we need that the 2 bits are the same. So that's what I depict by this solid line here. That just says we need A0 and B0 to be the same. If they are, then this probability will just be 1. The second probability says that in the 0, 1 case, we also need the bits to be the same. And in the third case, we have that A1 has to be the same as B0. But in the last case, when x equals 1, y equals 1, we're looking at these 2 value assignments, and we need them to be opposite. So we're looking for a valuation of these 4 bits that makes this pattern of correlations hold. But you can see just by looking at it that at most 3 of those 4 conditions can be satisfied, right? If A0 is correlated with B0, and B0 is the same as A1, and A0 is the same as B1, well then A1 and B1 also have to be the same. They can't be opposite. And similarly, for any way that you try to assign 0s and 1s to these 4 bits, you can only satisfy 3 of these conditions at most. So that's where this factor of 3/4 comes from. You can only kind of win this game or build a strategy of the sort that assigns at most probability 3/4 to this expression. And now I sort of said we're going to tentatively assume determinism, and we did that when we assumed that these things are sort of values rather than sort of arising probabilistically. But it's not hard to see that adding randomness can't help you, right? We're trying to generate correlations between Alice and Bob's outcome. If we're just adding some local randomness here within this box and some local randomness here within this box, that can't help you generate correlations between A and B. So there's no loss of generality in assuming determinism in this argument. You can show that it's just as general to assume determinism as not, and that's sort of known as Fine's theorem. It's quite simple to prove rigorously, but here I'm just appealing to your intuition that local randomness can't generate correlations. Okay, and I just want to mention that sometimes you'll see people draw the diagram in different ways. For example, they might draw it as a single classical variable that's copied and sent to Alice and Bob. Again, that's not any more or less general. All that it does is it changes this expression here from having sort of 2 hidden variables that are correlated to a single hidden variable. And so that means that here, instead of a distribution over these 2, you'll have a distribution just over the 1 lambda, and these outcomes will be a function of that same hidden variable. But again, there's the correlations achievable in this expression are the same as the ones achievable in this expression. That's not hard to see, so this is just a different way of expressing things. And it's one that you'll see often in the literature. People focus a lot on this condition here. They call it the factorization condition. Sometimes they'll say it's sort of the key assumption that you use to derive everything. But I would say, really, it's just a consequence of assuming this causal structure. It follows from this causal structure together with classical probability theory. Okay, so what we've seen so far is that if you assume this particular structure, and you assume that we live in a classical world governed by the classical GPT, then you're going to have to observe correlations that satisfy this constraint. That's what we've seen so far. What about if we live in a world described by quantum theory, as we know that we do? What correlations can we observe in this case? Well, a state on 2 quantum systems is associated with the bipartite density operator, rho AB. Alice's measurements are just some collection of positive operators, MA given X. Bob's similarly. And so we can write the correlations in this scenario now using the Born rule in quantum theory. So we trace the density operator with our measurement effect, which here is just M tensor N. And any correlation we can observe in this circuit will have to have that form there. And my claim is that, again, these correlations have to satisfy some constraints. The first constraints are exactly the same as the ones from before. They're the no signaling constraints. Doesn't matter if you're in a GPT world, a classical world or a quantum world, you still have this no signaling condition. Again, you can see that pretty immediately. Take this quantity, sum over A to compute this marginal on B. If you sum over A, well, the sum moves inside the trace here. and we're summing measurement operators over all of their outcomes, which by the properties of a measurement in quantum theory, that always sums to identity, which means we have this expression here, which you can already see does not depend on x. So the dependence on x has fallen out. We can even go a little bit further, and we can just notice that this thing, which describes the probabilities that Bob will get, they only depend on the reduced density operator on Bob's side, which makes sense. So there's nothing Alice can do on her side to change Bob's reduced density operator, so she can't signal to Bob. But if we now look back at that type of correlation that we considered before, we see that it's bounded, it has a different bound than what we saw in the classical case. And this is called the Searleson inequality. I'm not going to derive it for you. I'm just going to claim that the optimal quantum strategy can achieve a higher value of these correlations than could be achieved in any classical theory. In particular, you can achieve roughly 0.85. And one particular strategy that lets you compute this value is if you share this particular entangled state, it's a maximally entangled pair of qubits, then you have Alice do measurements in some complementary bases, like 0, 1 basis and the plus minus basis, and then Bob does measurements that are rotated by 45 degrees relative to those. And you can do the calculations here to find how large this probability is, and my claim is that it's about that 0.85, which is more than 3/4. And if you want to see this calculation done in detail, and just in general, 3 hours of lectures on Bell non-locality, again, that's a lot more than I'm going to cover today. I recommend also the talks given by Paul Skripchik at the last edition of this conference, where he goes through a lot of this in a lot more detail than I'll do here. So I recommend those. It's a really good introduction if you haven't seen this stuff before. Okay, so more generally, you can derive more than just that one inequality that I wrote down for you. There's actually a whole set of Bell inequalities for your given scenario. And just like in the non-contextuality case, an inequality tells you sort of that your data point has to live in a particular region of the space of probabilities for the experiment. And so if you have a whole bunch of inequalities and you have to live on a certain side of all those inequalities, you can show that the correlations consistent with this causal structure in a classical world are picked out by some region, which we call the local polytope. So any data point that satisfies all those inequalities lies inside this region. And once again, quantum theory predicts that there are points outside that set. And in fact, there are theories that can do even better than quantum theory, like box world that Rob talked briefly about. It can achieve an even larger value than quantum theory, all the way up to the logical maximum for that inequality that I talked about. And this is quite hard to see, I know, but if you observe a data point up here outside of the local set and inside, the quantum or GPT set, then you know that you're inconsistent with the hypothesis that the experiment is governed by the classical GPT and that the causal structure is the one that we thought it was. So in other words, if you observe a violation like that this quantity is greater than 3/4, then you know, so you can observe that in the quantum case, and you know that there's no such map into this classical theory because there's just no way to choose any stochastic processes here that can generate values like that. So this is an example where you see that regardless of whether or not you assume linearity, there's just no such explanation. And so this is an example of genuine non-classicality in the sense of the previous lecture. Once again, it's a sort of theory-independent certification of non-classicality, because the way that we derived this polytope, or that one particular inequality that I derived for you, it didn't assume the correctness of quantum theory anywhere, right? In fact, it was assuming the classical theory and then showing that you can't achieve that sort of violation within the classical theory. So that's the sense in which it's theory-independent. Okay, so what's the lesson now? Why is this revered as this great result within physics? What do we learn from these violations of Bell inequalities? Well, there's a few ways of thinking about it. The way that I've introduced things is I've said we've made two basic assumptions, that this is the causal structure, and we've assumed that the GPT governing this experiment is the classical one. Now, why are those good assumptions? Why should we be so shocked that one of these assumptions has to be false? Right? That's the conclusion of Bell's theorem. If you see a violation of Bell inequalities, then one of our assumptions has to be false. Why is that so surprising? Well, the first assumption, that this is the causal structure, is justified by relativity theory, which we have a lot of faith in. In particular, if we put Alice and Bob very far apart, then we can ensure that Alice's outcome A is not in the future light cone of Y. which means that if causal influences have to propagate within the light cone, as you would expect by the sort of relativistic speed of light bound, then there should be no causal influence from x to b or from y to a in this kind of experiment. And so we have good reasons to think the only way that a and b can be correlated is by some prior common cause that's in both of their past light cones. So we really believe in this causal structure for these experiments. But similarly, the assumption that the theory is governed by the classical GPT, well, this is justified by the traditional notion of scientific realism. Prior to quantum theory, all of our theories were assumed to be classical, and the basic sort of conception of science is that systems have properties. What are those properties if not just some set of possibilities? And how do we reason in the face of uncertainty other than classical probability theory? These are all like very well conceptually motivated concepts, and the fact that we have to give up either relativity theory or our traditional notion of realism came as quite a shock when people first saw sort of Bell inequality violations. Now, there's another framing that people often use of these assumptions. So sometimes we break up this assumption that this is the causal structure into a collection of smaller assumptions, which we often might think of as locality, and no retrocausality, and no superdeterminism. So I'm not going to spend too long on these, but roughly speaking, locality would be that there's no causal influences from x to events outside of its future light cone. No retrocausality just says that also there can't be causal influences backwards in time. No superdeterminism says that Alice and Bob can freely choose their measurement settings. In particular, that there's no correlation between what measurements they chose and the hidden variables governing what happens to the outcomes A and B. And that's a really compelling assumption when you realize that the way these measurement settings are often chosen depends on really absurd things that obviously aren't correlated with the sort of physical degrees of freedom here. Things like the digits of pi or the fifth letter in a poem that was written in the 1950s by some no-name author, right? Like you can do really absurd things to pick your measurement settings and make sure they're definitely not correlated with anything else in the experiment. So these all seem like pretty compelling assumptions. And then the final assumption is sort of that everything here is described by classical variables. Often people call this like the assumption of hidden variables or just classical realism. And so once you kind of frame things this way, well, then you can imagine the failure of each one of these individually, if you like. So for example, you could imagine the failure of locality. That would just look like the existence of some superluminal causal influence. So no matter how far apart Alice and Bob are, maybe the conclusion of Bell's theorem, one way to explain these violations is that there's some sort of hidden causal influence that's faster than the speed of light. Even though we don't know how to use that to signal faster than the speed of light, it could still be there in principle. Another possibility is, well, if you allow sort of backwards in time causal influences, then, well, now you can generate new kinds of correlations, because thus far when we drew this circuit, we were always assuming time went upwards. If you violate that assumption, then it's hard to see how that squares with relativity theory or common sense, but you can try to build such theories. Superdeterminism, once again, that you could imagine theories wherein, despite your best efforts to make sure this thing was really randomly chosen, somehow not only is it not random, but it's actually correlated with the fundamental properties of the systems you're measuring. It's a very conspiratorial thing to think if you choose your measurement settings in an intelligent way, but it's a possibility, logically speaking. Another possibility is maybe we should just give up altogether on the idea that we can give causal explanations. Maybe we should stop drawing these circuits and taking them seriously as pictures of the world. This is what you might do if you were an operationalist, and I think many people do kind of view Bell's theorem as a reason to stop trying to be a realist, because this is a strong challenge to our ideas about scientific realism. And this is what, so for example, Asher Perez, who Rob mentioned, said his conclusion from Bell's theorem was that unperformed experiments have no results. So by that he meant like you can't reason about the other cases, like you measured either 0 or 1. You picked which measurement to do. You're not allowed to imagine a counterfactual, like what would have happened if I'd picked that other measurement. Remember when we talked about 4 value assignments, like in this deterministic classical model, those value assignments would let you answer counterfactual questions, like what would have happened if I did the other measurement. Perez is saying, oh, you should never have thought about that sort of thing. You're only thinking that because you're a realist and you think there's really something fundamentally going on underneath. But his takeaway was, you can't say anything about what's going on underneath. Just try to make predictions and stop trying to explain what's going on. But the realists would say, well, that's giving up too quickly. Maybe you can still give causal explanations, and it's just the usual framework for causal explanation that we're using that needs modification. And that doesn't sound so crazy, given how much debate there already is about the nature of causation. So maybe we could build a framework for causation that goes beyond the usual kind of classical frameworks. And so there's kind of ongoing research these days looking for non-classical causal explanations. I'm not going to say what that means, but you can ask me later. And okay, so I want to just quickly note that this kind of approach to studying non-classicality can be done in a much wider range of scenarios than just the Bell scenario. So we call these like quantum classical gaps, because for all these different causal structures that you can study, the quantum correlations in many cases, such as these four, are a strict superset of the correlations you can generate if the circuit is described by a classical theory. And so that kind of allows you to see, once again, differences between quantum and classical theories. And as I've mentioned, that it gives you a way of ruling out the existence of any map, which in turn also rules out the possibility of a linear map. So I mentioned how that's a sort of necessary condition for classical explainability. And if you can show there is no such map, like you can do in all those scenarios on the previous slide, then just like in the Bell case, you have particularly strong manifestations of non-classicality. And a final thing I'll note is that you can also just think more directly. Rather than thinking about a comparison between two different theories, you can think about a comparison between the observed distribution and a single theory. So you can just ask, is the observed distribution compatible with the assumed causal structure and the assumed theory? And that's kind of what is often done under the name of causal compatibility. Okay, final slide. So just kind of comparing some advantages and disadvantages of these two kinds of approaches to studying non-classicality. Non-contextuality tests, according to my definition of classical explainability, are kind of a necessary and sufficient condition for classical explainability relative to the thing that I introduced in the first lecture. Whereas Bell-like tests make weaker assumptions and consequently are just sort of necessary conditions. Both of them have the advantage that they don't assume that quantum theory is correct, they don't assume determinism, they don't require perfectly pure states or perfectly projective measurements, which is good because you'll never have those in any real experiment. So those are advantages both of them share. Some more advantages of non-contextuality tests over Bell tests is that you don't require any specific causal structure or multiple systems. You don't require entanglement or incompatibility or freedom of choice or highly efficient detectors or space-like separation. So kind of all of these things you need in a Bell test. Those were all sort of implicitly built into the argument. Whereas an advantage of Bell tests over non-contextuality tests is that generally you don't require nearly as many measurements or preparations. So if you're actually doing the experiment, it might be much easier to build one particular entangled state and do 2 measurements on Alice's side and 2 measurements on Bob's side. Whereas in these non-contextuality tests, at least the state-of-the-art ones, you kind of do a full tomography on your systems, and that takes a lot more experimental capabilities. So that's an advantage of Bell over the others. So that's all I wanted to say for now. Once again, I recommend these lectures, and here's some more suggested readings. Thanks very much.
I saw that you drew non-contextuality and locality as overlapping, but isn't locality a specific case of context? So isn't Bell theorem a specific case of non-contextuality?